Hello everyone, welcome back. In this set of videos, we're going to really work through chapter 7.4, which is all about heat capacity. And in doing so, we're going to introduce a few ideas that are going to get really important over the next few sections. But for now, I'm going to kind of gloss over some of those ideas and save the details for later. Okay, so the first law of thermodynamics. This says that the energy, dE, the change of energy, is equal to the change in heat plus the change in work. So we're strange people as chemists. Q is heat, W is work. And these D's here that have bars through them, they indicate that these are inexact differentials. And we're going to learn more about that, but it basically means that they are not state functions. So now the change in work is really defined to be negative PDV, and Q is defined to be TDS based upon the relationship with this total differential that we derived in previous section. So we can see how the direct substitution works in this equation. Okay, so work. Let's talk about work for a minute. There are lots of different types of work. The main type that we are going to be focusing on is pressure volume work. And pressure volume work really is saying that inside of this area, something happens, and say a reaction happens and the molecules start pushing against the walls and this wall moves. I always think of this as a syringe, that as I put stuff into the syringe, that my volume gets bigger. As I take stuff out of the syringe, my volume gets smaller. And this is probably our easiest form of pressure volume work to be able to understand, because we can say that dW is going to be equal to negative PDV, and our equation has pressure and volume in the equation, which is the type of work that we're doing. But there's more types of work. So this idea of surface tension, if we take a drop of water, and we drop it down onto a surface, and it forms this bubble where A is the surface area and this gamma is the surface tension. This is a form of work. Chemical potential, this thing that we kind of keep mentioning but not really defining with the number of moles, this is another type of work. And so this is really talking about reactions and exchanging of a product for a reactant and changing the atoms that are within, or the molecules that are within a system. And that is a type of chemical work. There is also electrical work and other forms of work. But pressure volume is where we are going to stay and build our models around pressure volume work. Just know that what we figure out here can extend to other types of work. Okay, so when we start talking about energy and heat and work, we have to define heat capacity. The heat capacity is defined as the flow of heat per unit change of temperature. That's the PChem definition. The general chemistry definition, which remember we said everything in Gen Chem still applies. The general chemistry definition is the energy required to raise the temperature of 1 gram or 1 mole of substance by 1 degree is the specific heat. And so we can define this heat capacity as C, that is a function of temperature, which is defined to be equal to how the heat changes with temperature. So we're going to start with figuring out a derivation for what is the constant volume heat capacity. And in this, we're going to start with our definitions. We know that energy is equal to TdS minus PdV. We know the definition for heat capacity. And we also know our definitions for the change in work and the change in heat. So we're going to start with taking this equation. And I'm going to take the partial derivative of E with respect to T. And I'm at constant volumes I'm going to hold volume and the number of moles constant. So now if I basically I'm going to turn this portion into a partial derivative. And that's pretty simple since we already have derivatives. I have T, the partial of S, minus P, the partial of V, all with respect to T. Well, so in our system, we have said constant volume. That means that the change in volume is equal to 0. And so that means that this PDV term is equal to 0. And so this partial derivative is equal to TdS over the partial of T with respect holding volume and moles constant. Now, we already said that TdS is the same thing as dq, so I can go ahead and substitute this in. So dq, and I'm going to turn these to d's now, over dt, v comma n. And we said that this relationship that we just got is defined as C. And so CV T. So this gives us a couple of important relationships. One relationship is that CVT is equal to the partial of E with respect to T, holding V and N constant. The other is that dq is equal to CV dt. Well, constant volume systems come with some engineering problems. Heating a system at constant volume creates an increase in pressure. This increase of pressure can result in a very dangerous explosion. I can still remember one of the first distillations that I did in organic chemistry. I super wrapped the whole thing in aluminum foil, and I covered up the one vent port, And my professor came by and took one look at it, and he said, heating at constant volume is a bomb. Don't do it. So he's right. It is a bomb. And one example of this that has happened in recent history, one example is the Boston Marathon bombing. These used pressure cooker bombs. And basically, what they did was they put an explosive material connected to an electrical circuit inside of a pressure cooker. And so, this pressure cooker is very much a constant volume situation. And they would remotely detonate the explosive material inside, causing a ton of expansion, and eventually the expansion would burst through the walls of the pressure cooker, because it turns out that it takes a very robust system to be able to maintain heating at constant volume. And so because of this, in our next video, we're going to really talk about heat capacity at constant pressure instead, because that's something that we can manage a lot better.